Okay, let me clarify a few things on this project. So first of all, I think we neglected to tell you what M and N are in this. So M is the number of grid points or the number of intervals in the X direction. So the number of grid points including both boundaries is going to be M plus 1. Excluding boundaries would be M minus 1. And N is the number in the Y direction. So number of space in the Y direction. Okay, so this is M and N. And in question 1, in Jacobi and Gauss-Seidel, M and N is given for you, but on question 2, we neglected to give you M and N. And we are going to give you the M and N for question 1, so that like you can plot your stuff. And also, same as 4.1, in the question 2, we are giving M and N as inputs to your code. So you should be expecting any M and N. But in the first question, and also in the first question, we are going to give you what M and N that is going to be different from the M and N in 4.1. Also in question 2, you should expect our M and N to be a small number times certain power of 2. All right, so you don't have to, when you perform multigrid, you don't have to think of the special case where when you do multigrid to a certain level, it can go all the way to some very small number, where the number may be 3, maybe 5, maybe 7, but like basically it's close enough so that further iterations doesn't really matter. So in your recursive call, you can basically stop when either M or N is no longer divisible by 2. Okay. Any questions on that? Have all of you looked at the project, so you know what I'm talking about? Okay, good. And also on the test function over here, we didn't clarify what Xi is. Okay, so basically, Xi is a function that is a combination of Xi is a function that combines x, y, and t in a certain way that basically gives these as analytical solutions. So if you put a certain if you put like a times t plus b times x plus c times y and plug it in. So if you let Xi, let's say Xi equal to at plus bx plus cy, you can figure out there are certain combinations of a, b, and c that when you plug this equation into the governing equation, you're going to find out this is a solution. Right, and actually you can vary what a and b and c you give to the solution. For example, there is a combination where a is equal to 0. So the function is a steady state wave. That's good to test like your spatial discretization scheme, right? Because when you plug that solution and iterate to a steady state with a very big delta t, you should expect your solution to be similar to that analytical solution with the prescribed boundary conditions, with the boundary conditions that also satisfy the same analytical solution. All right, so we are going to also clarify that a little bit in the project. Any questions on this? Yes.
Does that analytical solution take into account the fact that there's a at the bottom?
That analytical solution, okay, good question. That analytical solution, you're going to see when you plug it in, it'll be, so you get a bump both at the top and bottom. For example, what I'm talking about is the one that like if you let a equal to 0 and figure out b and c, you're going to find out the analytical solution requires a bump both at the top and bottom. So you're going to get this, and first of all, that analytical solution only happens when you have a when you have a U0 that is greater than 1. So you're going to have a stationary wave that goes like this. You're going to have a bump at both at the top and at the bottom. Okay. So you're going to have something like this.
So for our case, U0 is 0.05.
Right.
What would be the expected?
So so U0 is 0.05, that means there is no, so that means there is no stationary solution. What you ended up having is you're going to have a wave. So you're going to have a that is not equal to 0, depending on your in some spatial direction. Not necessarily like that. So you may be going in this direction or that direction or that direction, whatever. But like your boundary condition is going to be a function of time. So you have a bump that goes through your boundary. Okay. Any other questions? Nope. Okay, so let's get into today's lecture.